Hello, college algebra kids. Today we're looking at absolute values and absolute value inequalities. Here we go. We're looking at section 2.6, last one in chapter 2. Notes out, and here we go. You looked at absolute values back in algebra 1, so let's define. If absolute value of x is equal to 5, what are the possibilities for x? What does that graph look like? Well, for the absolute value of x to be 5, remember x is equal either to 5, right? That's the number we plug in and make positive. That's 5. Or we can also plug in -5. Make it positive, and that's also equal to 5. What does that graph look like? Well, we have 5 over here and -5 here. Those are the solutions. Why are they the solutions? Because absolute value is a distance. The distance from -5 to 0 and 0 to 5, that distance is always 5. That's absolute value. Therefore, we have different types of absolute value equations we can write. For example, the absolute value of x is equal to k for k greater than 0. So this is the positive. If absolute value is equal to a positive, then we get two equations. Those two equations, just like this, are either x equals k or x equals -k. Therefore, the solution set is x is equal to the set -k and k. What if absolute value is equal to 0? Well, if absolute value is equal to 0, there is no distance, so that value is 0. So x is equal to 0, right? It could be something else inside that you have to solve. Therefore, the solution set is x equals the set 0. Note that's not the null set. That is 0. And the third option, absolute value is negative. So the absolute value is equal to k. If k is less than 0, that's negative. If we take a number and make it positive, can it be negative? No, that can't happen. So that is no solution. In that case, then, now we have the null set. So absolute value cannot be equal to a negative. Let's look at some example problems. Again, you did this in Algebra 1, Algebra 2. In general, for an absolute value equation, we're going to have the number equal to positive and negative. So we're going to write two equations. X minus 7 is equal to 2. First equation is the same without the absolute value bars. The second equation flips the sign of the number. X minus 7 is equal to -2. From there, we're going to solve. Therefore, x equals 9, and x equals 7 minus 2 is 5. Therefore, our solution set is 9 and 5. Same thing with letter B. In general, we're going to take the first equation will be the same. We're just going to drop the absolute value bars. The second equation, we're going to flip the sign. So 7 becomes a -7. We're going to solve just like always. 7 plus 5 is 12. -7 plus 5 is -2. Therefore, x is the solution set. 12 divided by 3 is 4. -2 divided by 3 is -2/3. Remember, order doesn't matter. This is not a solution, not an interval. This is a solution set, so order doesn't matter. Example 2, now we get into our options. Absolute value is equal to 0. Well, there is no plus minus because this is 0, so it's just the same equation. 2x minus 6 plus 7 is equal to 0. We're just going to drop the absolute value bars and solve. Distributive property gets us 2x minus 12 plus 7 equals 0. -12 plus 7 is -5 equals 0. Add 5. 2x equals 5 divided by 2. Therefore, our solution set is 5/2. Typically, I'll just go ahead and have you answer as an improper fraction because it's easier for you, and we're going to use that later on. So just answer as an improper fraction. Example 3. Again, we're going to start looking at some of the weird stuff that can happen. Letter A. absolute value of x minus 9 is equal to negative 6. Can an absolute value equal a negative? Never. That can't happen. Therefore, x is the null set. You're done. You don't have to do any work. You're just done. There's no solution. Letter B. Here we have algebraic stuff outside of the absolute value bars. So before we write our absolute value equation, we need to solve for the absolute value bars. So we need to solve for the absolute value bars. To do that, we're going to subtract 4 to both sides. Therefore, we have negative 5. Absolute value of 3x minus 7 is equal to 10. Here we want to divide by negative 5. Now we have the absolute value of 3x minus 7 is equal to negative 2. And we run into the situation again. Can an absolute value equal to a negative? It cannot. So therefore, x is the null set. There is no solution. Example 4. What happens if we have an absolute value on both sides of the equation? Well, in this case, we don't have a number to change. So what we're going to do is we're going to pick one side or the other. It doesn't matter which side we pick. And we're going to make 1 plus and 1 minus. We're going to write two separate equations, 1 plus, 1 minus. Again, it doesn't matter which side you pick. You'll get the same answers either way. So let's write the first equation, again, exactly the same without the absolute value bars. 2x minus 1 is equal to x plus 3. For our second equation, again, we're going to pick one side or the other. It doesn't matter which one. And we're going to make the whole expression negative. So there's our two equations. And we want to solve. So subtracting x is x. Adding 1 back is 4. The other side, we need the distributive property, the negative 2x plus 2 is equal to x plus 3. Add the 2x is 3x. Subtract the 3 is negative 1. Hang on a second. Let me check something. Therefore, x is negative 1/3. Oh, that should be a 1. Sorry. That should be a 1. So this is a negative 2. So we get a negative 2/3. Therefore, the solution set is 4 and negative 2/3. My bad there. Again, there's a check step. The check step would be plug the number back in and see if both sides are the same. So there's absolute value equations. What about absolute value inequalities? So these are going to kind of combine the last two lessons with inequalities with this lesson on absolute values. And here's going to be our general rule. So absolute value inequalities where k is greater than 0. Remember, if it is 0, it's just set equal to 0. If it's negative, you can't do it. So here we go. What if we have an absolute value that's greater than k? Well, graters, there's two of them, the greater than equal to. These two grators are going to turn into or graphs. Less than and equal to, and you can kind of hear it in the word less than. There's an and in there. Those two are going to be and graphs. So here's how this is going to work. So x is greater than k is going to turn into x is greater than k or x is less than negative k. So the first inequality is going to be exactly the same without the bars. The second one, we're going to flip the sign, flip the inequality symbol and the sign of the number and add the correct number. So this was an or. The solution set, we'll come back to. If we think about the graph, we would have a graph that starts at k and goes to the right. We have a graph at negative k that goes to the left. And so the solution set is going to be the union of the set negative infinity to negative k, union k to infinity. Equal to is going to be very similar. So again, to write the equation, we're just going to say x then is greater than or equal to k. The first one looks exactly the same. To get the second one, we're going to flip the inequality symbol. So now we have less than or equal to, and flip the sign of the number to be negative k. Again, greater is an OR graph. That graph is going to look similar. I'm going to go out and sneak that out here to the side. Again, at a positive k, now we are including the endpoint to the right. And at negative k, we're including the endpoint to the left. So that solution set is going to be negative infinity to negative k bracket union bracket k to infinity. Now for the less thans are going to be and graphs. So again, the first inequality is going to look the same. X is less than k. Less than turns into an and graph. To get the second one, again, we're going to flip the inequality symbol, turns into greater than, and we're going to flip the sign to negative k. Let's look at that graph. We have a positive k and a negative k. Positive is going to the left, negative is going to the right. There is our and graph. So you notice the graphs match what I said earlier. The first two are ORs. This is an and. So therefore, the interval has to be between negative k and k. The last option, same thing. The first inequality is going to look exactly the same. X is less than k. And x, we're going to flip the inequality symbol to be greater than or equal to. And we're going to change the sign to be negative. That graph, again, we're at a positive k to a negative k. We're going to the left of the positive, going to the right of the negative. So our solution set is negative k to k in brackets, because now we're including the endpoints. Those are the general rules that we're going to use for inequality absolute value equations. Let's look at some examples. Example 5, solve the absolute value of x minus 9 less than 2 and graph. First thing we're going to do is write our two equations. Again, the first equation looks exactly the same. X minus 9 is less than 2. Less than is an and graph. The second equation, the inside part stays the same. We're going to flip the inequality symbol and change the sign of the number. There's our equation. From there, we're going to solve. We're going to add 9 to both sides. So add 9 is 11. So x is less than 11, and x is greater than 9 minus 2 is 7. Right? Yes. We don't need to write the solution set. There's our solve. I guess we could. So what's our interval? Our interval is from 7 to 11. And we want to graph that. We're at 7 to the right, 11 to the left. We're not including the endpoint, so that's parentheses. And there's our graph. Notice the graph matches our solution set. Example 6, same thing. The first equation is exactly the same without the absolute value bars. 3x plus 5 is greater than 2. Which inequality is this? Greater is an OR graph. The second inequality is the same, but we're going to flip the inequality symbol. Now it's a less than, and the 2 becomes negative. We want to solve. So this is 3x. If we subtract 5, we get greater than negative 3. If we subtract 5, we get negative 7. Therefore, x is greater than negative 1, or x is, that was less than negative 7, or x is less than negative 7/3. What does that graph look like? Negative 7/3 is negative 2 1/3, so it's smaller than negative 1. So here's negative 1. Negative 1 is greater, so, and not including the endpoints, or going to the right. Negative 7/3 is not included, it goes to the left. Again, for the most part, all less than graphs will be and graphs. all gray torgraphs will be OR graphs. The solution set then is negative infinity to negative 7/3 union -1 to infinity. Example 7, solve and graph. Again, we're going to do the same process. We're going to write our two inequalities. First one is exactly the same. We're just dropping the absolute value bars. Second one, this is less than. That gives us an and graph. We're going to write the second equation, except we're going to flip the inequality symbol to be a greater, and we're going to change the 6 to be a -6. And we're solving. Subtract 5 is -3x less than 1, and -3x greater than -11. Solve, divide by -3. Notice what's going to happen. These are going to flip. So x is now greater than 1/3, -1/3. And it's still an and graph. X is greater, when I divide by the -3, the negatives cancel, 11/3. And because I divided by a negative, I have to flip. Ooh, almost missed that. What's that graph look like? Notice 11/3 is going to be a positive number. -1/3 is to the left. At -1/3, we're greater. We're not we are included. Missed that. So this is a bracket going to the right. At 11/3, we're bracket going to the left. Therefore, our solution set is -1/3 to 11/3. What are some other interesting? So here again is kind of the weird stuff that can happen. Some of the interesting things that can happen. Let's look at example 8. Here we have a 3 outside, 3 plus the absolute value, 7 minus 2x. An absolute value bar is greater than or equal to 3. We want to solve for the absolute value bars. How do we do that? Well, we're going to subtract 3 to both sides. Therefore, 7 minus 2x, absolute value is greater than or equal to 0. Well, if you look at this for a second, whatever number you plug in and make it positive, does it have to be greater than 0? Yes, because if you end up with a negative, it's going to be positive. If you end up with 0, 0 is equal to 0. If you end up with a positive number, positive numbers are greater than 0. So what do you notice? Doesn't matter what number you plug into this, all numbers have to work. So x is the reals. Our solution set would be -infinity to infinity. Now the tough part on this one is you can actually solve and get an answer, right? You can actually solve this. You would get 7 minus 2x greater than or equal to 0. So -2x is greater than or equal to -7. Divide, you flip, 7 halves. Doesn't matter. You have to see that on this inequality, once we get greater than or equal to 0, it doesn't matter what number you plug in, any number will work. Any number will work. This number actually has a different meaning, and that's in the graph. This is going to be the vertex of the absolute value graph. It actually doesn't have anything to do with the solution. So that's one weird thing that can happen. Here's the second one. Example 9. The absolute value, 5x minus 12, is less than -2. Now again, what does this absolute value say? Whatever number we get inside, we're going to make it positive. Is there any way that positive number can be less than -2? It can't, because it has to be positives. All positives have to be bigger than -2. This is no solution. X is the null set. So those are a couple of the weird things that can happen. Let's look at one application question. This question says the water temperature in a certain manufacturing process must be kept at 140 degrees Fahrenheit. So let's say at Hershey, they're making Heath toffee bars. They have to keep the water for making the Heath toffee bars at 140 degrees. Is that always possible? No. It can be a little bit hotter, a little bit colder. So the next part says the computer is programmed to shut down the process if the water temperature is more than 7 degrees away from what it's supposed to be. So the goal is 140. but we can go up to 147 and we can go down to 133. So we have kind of a 7-degree each way, 14-degree total, range of where we're trying to be. For what temperature readings is the process shut down? And I actually just gave you the answer. We want to look at this as an absolute value. What's X? X is the temperature to shut down. X is the temperature at which we want to shut down, right? If the temperature is 500 degrees, that's way too hot, we got to shut down. If the temperature is 100 degrees, that's too cold, we want to shut down. How do we find that out? We're going to use this formula. The temperature minus the goal is going to be less than or equal to the error, which is actually a common error formula. You might have seen that before in chemistry. Let's plug in what we know. What's the temperature? Well, the temperature is our variable. That's our X. Minus what's the goal temperature? That's 140. We want that to be less than or equal to our error. What's the error we can have? That is 7 degrees. There's our equation. It's a compound absolute value inequality. So we're going to solve just like we've been doing. The first one is exactly the same. X minus 140 is less than or equal to 7. So less than, that's an and. X is minus 140 is greater than or equal to negative 7. Now I want to solve. If I add 140, there is my 147. So for temperature readings is the process shut down. So here's the processes that work, right? We're in between this range. Anything between 133 and 147, we're good. What temperature do we shut down? So we're going to shut down for over 147 and under 133. All right, if we think about this as a graph, here's 133, here's 147. Here was our target of 140. The absolute value is the 7, that's our distance. So this is good. Anything else is shut down. So to the right is shut down, to the left was shut down. So there's one application of the absolute value inequalities. Your homework for section 2.6 is this, page 131, 16 through 38 evens, 56 through 72 evens, 78 and 80. Have a good day, Maroons. See you in class.